Hello, today we're going to look at solving a linear first-order differential equation. Previously, we looked at how to solve a separable ODE. However, if we look at the form of a linear first-order equation, such as this one, we will find it's not possible to rewrite it as a separable ODE. We may be able to isolate both the differential elements of x and y on either side of the equation, but the corresponding functions will not be completely in terms of either x or y. Notice on this side of the equation, we have the differential element of x, but the function that we're multiplying that differential element of x by is not completely in terms of x. It is instead both in terms of x and y. So instead, we want to find a function called the integrating factor so that when we multiply each term of the differential equation after it's been written in standard form by that function, we are left with an instance of the product rule on the left side of the equation, allowing us to rewrite it and integrate. We'll let p of x equal the integrating factor given by the function e raised to the integral of r of x dx. This equation may have been derived by your professor in class, or the derivation is located in your book. However, we will not go into that in this video and instead look at the technique. But before we do an example, I would like to talk first about a general linear first-order equation and what it means to write that equation in standard form. Suppose we have a function, general function, given by a sub 1 of x dy dx plus a sub 0 of x times y equals e of x, where a sub 1 of x, a sub naught of x, and e of x are continuous functions, and let's go ahead and assume that a sub 1 of x is not equal to 0. What we do is we divide each term in the equation by a sub 1 of x. Now we have a coefficient of 1 in front of our leading term dy dx. Next, we want to define r of x as a sub naught of x over a sub 1 of x. And we'll define q of x as e of x over a sub 1 of x. Rewriting, we are left with dy dx plus r of x times y is equal to q of x. Now our linear first-order equation is written in standard form. Now let's solve the linear first-order equation we started with. Suppose we have the equation x times dy dx plus 1 plus x times y equals 1. First, we want to write this linear first-order equation in standard form. We do this by assuming x is not equal to 0 and dividing each term in the equation by x. X over x reduces to 1, leaving us with dy dx plus 1 plus x over x times y equals 1 over x. This here is going to be our r of x, which we'll use to find our integrating factor. So if we come over here, r of x is equal to 1 plus x over x, or 1 over x plus 1. Let's find our integrating factor by raising e to the integral of 1 over x plus 1 dx. Integrating, we have ln of x, absolute value of x, plus x, which simplifies into ln of absolute value of x times e to the x, which is x times e to the x. Now we'll take this function and multiply each term in the differential equation by that function. So we're left with x e to the x dy dx plus our x is reduced to 1 e to the x times 1 plus x times y, which equals, same over here, our x is reduced to 1 e to the x. Notice now on the left hand side of the equation, we're left with an instance of the product rule of the function y times x e to the x. So now we can rewrite this as x e to the x y equals e to the x. And if you'd like, you can go ahead and apply the product rule to this function, and you will find that you end up with the left-hand side of our equation. Now, you can multiply both sides by dx and integrate both sides of the equation. This leaves us with x e to the x times y equals e to the x plus c. Divide each term by x e to the x to get our explicit solution. And our final answer is y equals 1 over x plus c over x e to the x.